Hi everyone, welcome to lesson 13 of Advanced Higher Stats course. In this lesson, we will be looking at the standard error. You will find this skill on page 24, 25, and 26 of the Advanced Higher course spec. By the end of this lesson, you should know the difference between sample and true values, to understand the difference between the two standard deviations, to understand the use of and how to calculate standard error, and you should understand what the central limit theorem is. The way we differentiate between sample values and true population values are through the notation. So for example, the sample mean would be written as x bar, whereas the true population mean would be written as mu. Similarly, the sample standard deviation would be written as S and is calculated a slightly different way, which we'll look at later. And the true standard deviation is written as sigma. So that would mean sample variance is S squared and true variance is sigma squared. Why should we know about these two types of categories? Well, sample values can be very deviated from the true values, and that could result in invalid statistical analysis. So our goal should be to get as close to true values as possible, and that might not always be possible, but we should try our best. And there are a few ways we can do that. One is by increasing our sample size. This would give us a better generalization of the population. Another one would be using standard error. This would make up for any differences we have, or try to make up for any differences we have between our sample deviation and our true standard deviation. Another method could be to use random sampling techniques to not have any skewed data and to reduce measurement error. So any machinery we're using, we should make sure that they are rounding the right way. And here's an example of what a sample normal distribution and a true normal distribution can look like for a population. So you can see here, this could be the true one, but when we're sampling, maybe our sample is a bit too small and it's a bit not valid enough, and we get a mean that's much smaller. So this is around 9.35, whereas this is around 10, and that's a pretty big difference, and especially with their spread as well. And if we do any statistical analysis, it would not be as valid as we would originally think. One way the validity of statistical analysis is improved for sample data is through how their sample standard deviation is calculated. So in National 5, you would have also done it this way. You would have done the n minus 1 uh, as the denominator. But how population standard deviation is done is just with n, just with the sample size as a denominator. So what this n minus 1 does, it increases the sample standard deviation. So when you disprove a null hypothesis and do some hypothesis testing, you are more likely to be correct and not have a false positive. Now let's try this question. The height of men is normally distributed. From a sample of 50, it was found that 82.5 meters was the total height of every man, and sigma is already known to be 2.5. Write the parameters of the distribution. So how you write this is we would write x bar, this shows that this sample data is roughly equal to this normal distribution, which is we need to divide 82.5 by 50, which gives us 1.65 meters and 2.5 squared. And this is how we would write the parameters. So we need to make sure that we write this bit here because this shows that we're getting it from a sample and it's not a true normal distribution. Now let's move on to standard error. Standard error is used for hypothesis tests, confidence intervals, and comparing means and proportions. It's used when either sigma or mu are unknown, or even when both are unknown and you've calculated it. If you know sigma but you don't know mu, this is the formula. If you don't know sigma, then regardless if you know mu or not, this is the formula here. And it's the same thing, it's standard deviation over root of the sample size. And how you would reduce this is by having a greater sample size, and we're assuming the standard deviation remains constant. Try this question. The height of men is normally distributed. From a sample of 50, it was found that the total height was 82.5, and the sample standard deviation was 2.2. Write the parameters of this distribution. So we have to make sure that we're writing x bar, and then these squiggly lines which show that it's roughly similar. And then we do 1.65 and 2.2 squared, because the variance goes there, so it's sample standard deviation squared. What percentage of men are below 1.7 meters? And here we use standard error. So we use the formula here on our left hand side, which is we can replace with 1.7 minus 1.65, the average height, over our sample standard deviation, which is 2.2, root over root, and the sample size, which is 50. And that gives us 0.16. And then we find the probability of z being less than or equal to 0.16. We look on our table, 0.16, so 0.5636. 0.5636, and that would be our answer. So it's very similar, just need to make sure that in a question we know that it's a sample, and when we know it's a sample we use our standard error instead of our sigma. Now, the final question I have for you today is, can we still use this formula if the population distribution isn't normal? Why or why not? And I want you to pause and kind of think about this for a bit. For example, if the population distribution was something like this, could we still use the standard error that we've been using and all these formulae? Can. And that's because of the central limit theorem, which states the sampling distribution of the mean will always be normally distributed as long as the sample size is large enough. And according to the advanced hardcore spec, 3 criteria have to be met for this to happen. N being greater than or equal to 20, NP being greater than 5, and NQ being greater than 5. These are the same criteria that has to be met for the binomial distribution to be approximated to be a normal distribution. And if these criteria are met, any sample we've gotten, we can treat it as approximately normal. At the end of the lesson, we will look at standard error more during hypothesis testing. By the end of this lesson, you should know the differences between sample and true values. You should understand the difference between sample standard deviation and true standard deviation. You should understand the use of and how to calculate standard error, and you should understand what a central limit theorem is.